Just a second, I need to double check. Second. Hello, welcome again to Tuesday seminars at the Warsaw University Astronomical Observatory. Today we have an honor to have a guest, a real guest, in real person, Henryka Netzel, who did her PhD recently in Copernicus Center here in Warsaw, and now is a postdoc in Konkoly Observatory in Hungary. And Henryka is going to tell us about asteroseismology. Really, please.
So, hi, for those of you who don't know me, I did my master's here, so it's really nice to be back, so thank you for having me. And I will be talking about the research that I did as a part of my PhD, so that was asteroseismology of stars from the classical instability string. So I will be talking about stellar pulsations, and we can divide pulsations into radial and non-radial. In the case of radial pulsations, we have a star that is expanding and contracting periodically, but the spherical shape of the star is preserved. And if the star is expanding and contracting, we talk about the fundamental mode. If there is a node inside of the star, we talk about the first overtone. If there are two such nodes, second overtone, and so on. In the case of non-radial pulsations, the spherical symmetry of the star is no longer preserved during the pulsations. You have several examples here, how the geometry could look like. And here, blue and red corresponds to sectors of the star that move into opposite directions. And non-radial pulsations we describe with two numbers, L, which is a degree of the mode. And degree of the mode tells us how many of nodal lines are there on the surface of the star. These are those white lines here. And another number that we use is M, which is an azimuthal order of the mode. And this number tells us how many of those nodal lines on the surface cross the equator of the star. So pretty easy. We have pulsating stars all over the Hertzsprung-Russell diagram, like you can see here. Stars can pulsate in various stages of evolution, but I am interested in stars that are located here on the so-called classical instability strip. And here for lower luminosities, we have our Lyra stars, and for higher luminosities, we have Cepheids. And these stars, as you know, they are extremely important tool in astrophysics, but for asteroseismology, they were not so useful because huge majority of them pulsate in one or maybe two radial modes. And in asteroseismology, we compare the pulsations as we observe with theoretical models. So to have good constraints on the models, we need many modes, and one or two is simply not enough. So with some exceptions, like for example, triple mode Cepheids, where we have 3 modes, so we have some reasonable constraints. These stars were not really studied with astroseismic techniques. But over the recent years, in these stars, in some of them, we detected some additional signals. And we think that these additional signals are due to additional non-radial modes. So if we have identification of these modes, which means that we know those numbers, like a degree of the mode, then we can compare that to models, have additional constraints. So the stars with those additional signals that we have discovered, they give us the very first chance to really use astroseismic techniques on large number of these stars. So I will be talking about multimode pulsations. So it is the most convenient to show them on the Petersen diagrams that you see here. So we have for our large stars and for classical Cepheids. And on the Petersen diagram, on the y-axis, we have period ratio of shorter to longer period versus longer period or logarithm of the longer period. And in multimode pulsations, those period ratios that we observe, depending on which modes we have, they put those stars in groups, as you can see here. So for example, this green group, these are stars that pulsate in fundamental mode and first overtone at the same time. But I am interested in stars that are located here. So in these stars, they are observed both for our stars and classical Cepheids. The period ratio is characteristic around 0.61. So I will call these stars 0.61 throughout my presentation. And in these stars, what we observe is that the dominant mode of pulsations is the radial first overtone, and we see additional signal that has low amplitude, shorter period, and forms this characteristic period ratio. And also what we see here on Petersen diagrams is that both of these groups show 3 sequences inside. So it's not as well visible for our larger stars, but there is a sequence in the middle. And here we have for classical Cepheids very nicely resolved 3 sequences. So because this period ratio is around 0.61, we knew straight away that this is not pulsations in some additional radial mode. And here is a proof of that. So here we have a zoom into the region on the Petersen diagram where our larger stars are. And these black crosses, these are 061 our larger stars that were new in 2015. And those colorful points, these are models for 3 different metallicities. And on top, we have period ratio of the 3rd overtone to 1st overtone. And in the bottom, we have period ratio of 4th overtone to 1st overtone. And these stars fall exactly in between. So we know that this is not due to radial pulsations. So it has to be due to non-radial pulsations. So what we see in frequency spectra, where we have amplitudes as a function of frequency, in these stars, we have the dominant signal that is due to 1st overtone and its harmonics. We see the additional signal that has longer frequency, low amplitude, and forms this characteristic period ratio. And in some of the stars, we see also its subharmonic. And subharmonic is a signal at half integer frequency. So here is a half of this frequency of this red signal. Also, in some of these stars, we see more than 1 additional signals. And if you remember, there were these 3 sequences on the Petersen diagram. So a star like that would fall into all of these 3 sequences. And here is an example of how it looks like in the real star, in real data. So in the top panel, you have a zoom into the frequency range where those additional signals are. And in these stars, we actually see those 3 signals that puts the star in 3 sequences. And here the horizontal axis is scaled with the period of the 1st overtone. So we have period ratio 061, 062, and 063. And that's the locations of those sequences. And in the bottom, you can see the frequency range corresponding to those subharmonics. So for one of these signals, we see signal at half of this frequency. And also, what we can see here, what's really important, is that those signals are not single peaks. They are a bunch of peaks. And in the case of subharmonics, they are like power excesses. They are pretty wide. And that means that in the time domain, the amplitudes and frequencies of those signals just change in time. Okay, so the explanation of what we see in these stars was proposed by Professor Dziembowski in 2016. So what he proposed is that what we thought was a subharmonic is an actual non-radial mode that is present in these stars. And due to several reasons, it's easier to detect its harmonic, which usually has a higher amplitude. So he calculated models that you can see here with those lines, and they fit very nicely those sequences. So in the case of our Lyra stars on the left, the top sequence is explained with the harmonic of the mode of degree 8, and the lowest sequence of the mode of degree 9. The sequence in between is just a combination of those two. In the case of classical step-8s, they are explained with harmonics of non-radial modes of degrees 7, 8, and 9, starting from the top sequence. So it fits very nicely. And just to show you in frequency spectra again, what we thought was a subharmonic, this green signal, is a non-radial mode according to this explanation, and we usually just observe its harmonic. That forms period ratio 0.61. Okay, so I used the Ogle data for the galactic bulge to search for those 0.61 Lyra stars, and I found nearly 1,000 such stars, which is a very nice sample. And here we can see the zoom into the Petersen diagram for this group. So very nicely we see those three sequences at 0.61, 0.62, and 0.63, where the lowest sequence is the most populated one. On the right panel, that's a distribution of period ratios, so we can see that they are very nicely separated. So with such a huge sample, I could test the predictions of the model that was proposed by Professor Dziembowski. So in this model, where the subharmonics are non-radial modes, it's really important to have stars that have subharmonics. So I detected those subharmonics in 114 stars from the sample. Just to remind you, these are those signals at the lower panel. And if the model is correct, that this theory is correct, basically it should be easier to detect non-radial modes of degree 8 than of degree 9. Why? So if we have those surfaces of the star that are divided into different sectors that move into opposite directions, the higher the degree of the mode, so the more sectors, then the amplitude cancels out from the surface. So the higher the degree of the mode, the more cancellation effect is important. And this is shown. So on the y-axis, we have the cancellation factor, which basically tells us how the amplitude is lowered because of this effect of cancellation of different factors as a function of the degree of the mode. So for L equals 0, we have radial modes, we don't have any cancellation. But we are interested in those 8 and 9 modes. So basically, the non-radial mode of degree 8 is less affected. So it should be easier to detect that because it should have higher amplitude. And I tested that. So in the context of those additional signals and subharmonics, basically what it means that we should detect more subharmonics to the signals that fall into the top sequence. That's what is predicted. And this is exactly what we observed. So here on the Petersen diagram with black, I plotted stars in which we do not see subharmonics, and in red, those stars in which we do see subharmonics. And indeed, they are mostly fall into this top sequence. So this is exactly how it should be if the model is correct. And also very interesting group here are those blue stars, because in these stars, the situation is like that. So we do not see those additional signals that form period ratio 0.61, but we see the signal that would be a subharmonic, which would fit very nicely if these are those non-radial modes. So maybe these are stars in which we see only those non-radial modes. And they also fall very nicely to the top sequence if we calculate what would be the period ratio of those additional signals. So another argument in favor of the model proposed by Professor Dziembowski is this. So here is a distribution of the amplitude ratio between those subharmonics and those additional signals. And in 34% of the stars from my sample, in which we have subharmonics, the amplitude of the subharmonic is higher. So it is also a strong argument that these are not really subharmonics, but they are really signals that cause the variability. Also, as I mentioned in the introduction, those signals are wide. They are not coherent peaks. They are wide bunch of signals. And what it means that it varies in time. So here is how I tested that using the oval data. So again, now in this panel, we have the range in the frequency spectrum for data collected from 2010 to 2015. And we have this range corresponding to additional signals. This red line marks roughly the detection threshold. So in this chart, we see very nicely, we have 3 signals falling into those 3 sequences. But I took those 6 years of data and analyzed them year by year. And the picture is completely different. So here, starting from here, we have 2010, and we see only 2 signals. Then in 2011, we see 3. In 2012, on the bottom, we see only 1 signal. Then again, in 2013, we have 2 signals. Then we have again 1 signal. And then what is really interesting, in 2015, there were no detections at all. So if we had only those data, even though this is a very nice star that falls into 3 sequences, with only data from 2015, the star wouldn't be even classified as a member of this 061 group. So you can see how variable these signals are, but it can be much better tested with space data, much more in detail. We can investigate how those amplitudes change. So in the original Kepler field, there are 4 RC stars, and all of them have those additional signals. And here we have each panel for each of those 4 stars. On the y-axis, we have the amplitude and as a function of time. And in blue here, we have amplitude of those additional signals that form those period ratio 0.61. And in red, we have subharmonics at half of the frequency and 1.5. So there is a lot of variability going on, which is not strictly periodic, and also the variability of those additional signals and subharmonics are not really correlated. And this is what forms those really wide peaks that we observe in frequency spectrum. Okay, so we have a lot of stars in which we observe those additional signals, and we have very nice theory explaining that, but there is still no direct mode identification. And one way to do that would be to use spectroscopic data. The question I also try to answer for those stars, if these are indeed those non-radial modes of relatively high degree of 7, 8, and 9 in Cepheids, can they be even detected in spectroscopic data? So to answer that, I simulated line profiles in synthetic spectra and how they change due to the pulsations, because this is the method that we use to later identify those modes. So for the calculations, I used a star, a classical Cepheid, that is in a binary system, in an eclipsing binary system that was studied by Pilecki and collaborators. So because it's an eclipsing binary system, I had physical parameters determined very well, so it was a perfect example to use for the calculations. And here is an example of how those line profiles change because of the pulsations. So here we have a few line profiles that are affected by pulsation in the first overtone. So the profile just moves left and right. And here we have variations of those line profiles due to pulsations in first overtone and additional non-radial mode here of degree 7. And there's not much difference between the two, but if we subtract one set from the other, there is indeed a difference caused by the presence of the non-radial mode, but this is an extremely subtle effect of very low amplitude. So the question is, if we add noise and if we add gaps into those observations, is that even detectable? So this is what I tried to test. And I tested 2 cases. First was a perfect noiseless case where I didn't include any noise. I had constant observations without any gaps due to bad weather or even night. And that was and I didn't include any noise, obviously. So that was to test how the different parameters like the azimuthal order of the mode or the inclination would change the detectability. And then I tested a realistic case, And then I included gaps into observations and I added noise. So here's an example of how, in this perfect noiseless case, what's the effect even of changing the azimuthal order of the mode. So here we have the amplitude and the azimuthal order for a mode of degree 8. And in blue, we have amplitude of the non-radial mode. And in red, we have amplitude of its harmonic. So if the azimuthal order is 0, the highest amplitude is of the harmonic of the non-radial mode. And then it falls down the amplitude. But for n equals 1, it's the best parameter to detect the non-radial mode itself, then the amplitude is the highest. So I tested several cases like that, and then I moved to testing realistic cases. Here's an example of an example sampling that I used. So we have 60 nights with those gray stripe marking the breaks due to days, and from those 60 nights, I randomly selected 40 nights. I took 5 spectra each night, and this is just an example of the sampling that I tried. And here, I also tried the spectra that were taken by Pilecki and collaborators who started actually this system. They had around 50 spectra, so this is how they are distributed in time. So I also was interested if the spectra that are already there, can we detect some? So here is a table with some of the results. So we have a non-radial mode of degree 8 as the additional non-radial mode. And in the first column, we have azimuthal order. So now it's always 1 because it's the best scenario. Then we have number of nights, so 50, 40 selected of 60, and coming from Pilecki. Number of spectra that were taken, so that was over 200 or 50. And then we have signal to noise of those spectra, the average signal to noise. So no noise means no noise. And then we have 300, 200, which means declining the quality of the spectra. So yes means there is a detection, no means there is not. If we do not add any noise, there is obviously a detection. If we have 300 signal to noise, we also have a detection, but with 200, there is no detection for Pilecki and collaborators. And so if with 200, there's no detection, and the average signal to noise was like 20 in the spectra, so that's no surprise they didn't detect anything. 150, only with over 200 spectra, there was a possibility of detection. And here's an example with the azimuthal order of 0, where the amplitude is smaller. So without noise, only with 50 nights of observation, there was a detection. With timings of Pilecki, it was not possible to detect any signal, even though I didn't include it anyway. So it shows that it's extremely challenging. Basically, it would be possible if we have a lot of spectra with extremely high signal to noise, but it will be a challenging task to do that. So we do not have direct mode identification, but the observations of this large group of 061 stars really supports the model proposed by Professor Dziembowski. So if we assume that this model is correct, we know the identification of those modes. So with this assumption, we can model those stars and check the results if they are reasonable. So this is what I did. And the number of stars for modeling was relatively high. It was like around 50. It wasn't a detailed modeling of individual objects, but I used the grid approach, which means that I calculated a large grid of models. And then from this grid of models, based on period and period ratios, I selected the model that fits best to the observed period and period ratios of the star that I wanted to model. So those models were calculated with the Warsaw envelope code. And envelope code means that only the envelope of the star is modeled. And with those modes, we can do that. And it has some advantages and disadvantages. So disadvantages are that we are disconnected from the evolutionary theory. We don't have to have the proper evolutionary model. We just give parameters, we have the envelope model. But it also has some advantages because there are uncertainties in the evolutionary theory on its own. So we are disconnected from that, and later we can compare the results. So it has pros and cons. Here are the parameters of the grid that I used. So masses from 0.5 to 0.9. Luminosities, I changed luminosities, effective temperatures, and metallicities. And the whole grid consisted of over 2 million of models, so it was pretty dense, so quite good for the modeling. And so I had those models, and I had to get those edges of the instability strip, and I took that from the literature, from the work by Marcani and collaborators. So here is how this grid looks like on the Hertzsprung-Russell diagram. So those blue and red lines, they are edges of the classical instability strip for 3 different metallicities, and the points are the models. And here, in black, we have models in which the first overtone is unstable. In yellow, where the fundamental mode is unstable, and in pink and blue, where those non-radial modes are unstable. Pink for 8 and blue for 9. So what is straight away really interesting here is that we have a lot of models in the middle of the instability strip and closer to the red edge, where those models are unstable. So here we have models where we could observe those non-radial modes, but closer to the blue edge, we do not have those models. So we do not see non-radial modes close to the blue edge. And this is really interesting from 2 observational results points. So first, we didn't know at the time whether all those Arlary stars and classical Cepheids have those non-radial modes. Maybe all of them have, but they are so low that we cannot detect them due to noise. Because if the quality of the photometry is better, we have the higher incidence rates of stars where we do see those non-radial modes. So with the ground-based photometry, depending on the quality, it's around 10%, where we have the detection up to 60. But with space-based photometry, we have 100, especially for those 4 stars in the original Kepler field, where the photometry is amazing. We have detections everywhere. So it wasn't clear whether all of these stars should have that. And also, the second thing is that we had some data from globular clusters, and here we have the color magnitude for the globular cluster M3. And in blue, these are stars that have the first overtone, and with pluses inside, these are stars in which we have a detection of those signals. So we don't have any detections at the bluest part. And here is another color magnitude example for globular cluster NGC 6362. Again, circles, these are first overtone stars with pluses detection of those additional signals. And again, don't mind this star, but at the bluest part, we don't have any detections. And here is the last example for the sample from test. Again, now we have blue diamonds, first overtone stars with the border detections. So the errors are larger, but the trend is the same. So the incidence rate of detection is lower, closer to the bluest part. And this is exactly how it fits to the grid of models. So indeed, close to the blue edge, we do not have non-radial modes that are unstable. So it fits very nicely to what we already observed in the globular clusters. Okay, so I took this whole grid of models and I compared that with the stars that we observed. And for the input sample for the modeling, I chose stars that are at least triple mode. So these can be either RC, where RC means first overtone pulsations and 2 non-radial modes, so 8 and 9, or RD, where we have pulsations in the radial fundamental mode and first overtone, and at least 1 non-radial mode. So the input samples were from 4 sources, so RRC stars from the bulge and RD stars from the bulge that I analyzed, some additional K2 RC stars, so from this K2 mission by Kepler, and some additional 061 Arlary stars from the literature, like from those globular clusters that I just showed. And for each of those stars, I picked the model that had the closest periods and period ratios, and I got parameters like the masses, metallicities, effective temperatures, and luminosities. And here the results are presented in the Hertzsprung-Russell diagram. So again, we have blue and red. These are theoretical edges of the classical instability strip. And those samples that I used for the modeling are plotted in different colors. So we have, in green, we have our C stars. With cyan, we have our C stars from K2. With blue squares, we have our D stars with non-radial mode of degree 8. And with red triangles, non-radial mode of degree 9. And there is one orange star here, RD, that's located here. So this is the star in which we have fundamental mode, first overtone, and both non-radial mode. So we have 4 modes, so it's perfect. Okay, and here we have also those gray lines. These are lines of the constant period. So here we have period of the first overtone around 0.31 days and 0.35, slightly longer here. So majority of our C stars, they have periods of the first overtone around 0.31, and typically our C stars from the Kepler, they have slightly longer periods of the first overtone. And it is interesting, after I got these results, and that would be really interesting to compare that to some other estimation of parameters. Unfortunately, we do not have any direct estimation of mass for our Lyra star. We don't know any Lyra star that is in an eclipsing binary system, but we can compare the metallicities because we have spectroscopic metallicities for our Lyra stars. So here is a distribution of metallicities in blue for our C stars, so first overtone our Lyra stars in the vicinity of the Sun. And in red dashed line, these are metallicities that I got from the modeling. And it is very nice that the distributions are similar and they both peak roughly for the same value of metallicity. So it's reassuring that the assumption that we made at the very beginning of the modeling, that these are those non-radial modes of this identification, that this is true. And because the metallicity fits, we now can discuss the masses for which we do not have any other way to compare them. So here is a distribution of stars that I modeled. On the plot where on y-axis we have observed period of the first overtone, and here there is a mass from the modeling. Again, stars are divided by color to those different input samples. So the majority of stars and majority of our C stars from the bulge, they have masses around 0.7. We have some stars with the lower masses, and what is interesting, we have those stars here that have masses above 0.8, which is higher than what we would expect for our Lyra stars, and they have they consist of stars from the K2 mission and RD stars with the non-radial mode of degree 9. RD stars that have non-radial mode of degree 8 or both, they also have those masses lower than 0.8. And also what is interesting in these stars that the only observational difference between those stars with high masses and like regular masses is that they have longer pulsation periods. Okay, so here is again the results on the Hertzsprung-Russell diagram, but now in these are all the stars that I modeled, and the color corresponds to the mass. So we have again majority in 0.7. We have some stars that have lower masses, and for the highest luminosities, we have stars with the highest masses. And now we can compare that to the evolutionary theory. So this is a rough comparison of the stars that I modeled with the evolutionary tracks of the horizontal branch stars. And on the left panel, these are tracks from the Basti database, and on the right from the Dartmouth database. For 3 different metallicities, so solid line is the lowest, the highest metallicity. Then we have dashed line and dotted line for the lowest metallicities. And the color of those tracks is also, again, from this legend. So we can roughly compare the same position of the Hertzsprung-Russell diagram. What are the masses? And we arrive at the mass discrepancy problem between the pulsation theory and evolutionary theory. Because if we look, for example, here, we have a track that has lower mass than the mass that I got in the pulsation modeling. So this is really interesting to study further, especially that if you compare those two panels, there is also a discrepancy between the tracks from the evolutionary theory. And also, another way in which I could compare masses to some other estimates is that there are methods that connect physical parameters to the light curve shapes. And this is what Simon and Clement proposed, that the mass of the star can be a function of the parameter phi31, which basically describes the shape of the light curve, the period of the first overtone, and helium abundance. So they prepared the relation, but if I use this relation, for all of the stars, I got masses below 0.45, which is even lower than what we would expect. So there are discrepancies based on those methods, different methods, so that would be interesting to study further. And yeah, so to conclude, we know a lot of those stars in our Lyra group and classical Cepheids group that have those additional signals. And the observations and the properties of those stars really support the model that was proposed, that these are due to those non-radial modes of degrees 8 and 9 or 7, 8, and 9. And that allowed us for the first time to use those stars for the asteroseismic modeling. And for majority of stars, we got reasonable results, but it will be obviously interesting to study further with some additional observational constraints like the metallicity for those stars to get some additional constraints on the model. Thank you.
Thank you. Thank you very much. Questions here, please. Let's start from the audience here.
I have two questions about spectroscopy.
I think if you could come forward, because the microphone is here, so we want to have you recorded. Sorry. This is enough.
Okay, so two questions about the spectroscopy. First is related to this Cepheid star of Pilecki et al. Don't you think that the second component of the star would affect the spectra itself, that could make some problems with getting this proper harmonic signal of the pulsation? Does it affect anyhow the spectra in these terms? And the second thing is related to actually the last part of your talk. Could you use spectroscopy to somehow get the idea about the masses of early Lyra stars that you are working on? Is it somehow helpful that the spectroscopic models, atmospheric models, could be helpful in that, or not really?
Well, so far, nobody did that. So yeah, we should have like the binary system, eclipsing binary system to get the the proper masses, like the direct mass, so that we don't have any more assumptions and so on, but we can really compare that to. And with the first question, that's not a really close system, so I don't think so. But it will be actually interesting because this is a star that pulsates in first overtone, and we assume that majority of those stars have those additional signals. But in this star, in photometry, there is no detection. So that might be interesting. That being in a binary system, it changed something. But yeah, but it's not so close that it should affect. I don't think so.
Thank you. Any other questions? Please come forward.
I remember you said that Cepheids are like too calm or basic to study, but are there maybe plans to study at different stars besides earliers in this main instability strip? They could maybe help us understand star dynamics more.
Yeah, all of those groups that I showed in the beginning. This.
I don't know, but are there plans to study in your project further, any of them?
With those additional signals, exactly those. Yeah, so we do not see that in other objects. So we have them in our library stars, in classical Cepheid, and there's one in an anomalous Cepheid. So this is like the very unique to this. And obviously other stars also have non-radial modes, but this is not exactly what we are interested here. So.
Okay, thank you.
So you showed for our varieties, the L equal 8 and L equal 9 lines on the Petersen diagram, and there was a group of stars in between that you said are combination of these two, L equal 8 and L equal 9.
Yeah.
Yeah, but you had models, yes, before, yes. So what combination here means? It means that they pulsate both in L equal 8 and L equal 9, and we see only one period, or there's...
So if we have...
What's the middle group?
The middle group. Okay, so let's look here. So, or maybe here, yeah. So here we have the non-radial mode, which can be degree 8 or 9. Here we have the harmonic of the degree 8, here we have harmonic of the degree 9, and this signal is a frequency of non-radial mode of degree 8 plus frequency of non-radial mode of degree 9. So even though because this signal has usually much lower amplitude, and from the geometrical cancellation and so on, these signals are much less affected. So sometimes we do not see those non-radial modes, but we see the combinations that they make.
Okay, I'm bringing up the Zoom window. Are there any questions on Zoom? Please raise your Zoom hand. Yes, please.
Hello, Henryka. Thank you very much for your talk. I would like to ask you about your opinion of observing RR Lyrae stars in globular clusters to find more of these extra signals, because in a globular cluster, at least you see where in relation to each other these stars are, not like in oval where it's just an amalgam of stuff from before the bulge, in the bulge, and after the bulge. So like you don't even know really what the individual luminosities of each of the stars are, right?
Yeah, exactly. That would be really great to have more stars in globular clusters. I included in my sample stars from M3 and NGC6362, but unfortunately I had to select only those stars that had 3 modes, and I have only 2 stars from M3 and only 2 stars from NGC6362. And it would be amazing to have more of them because we have roughly the same metallicity and so on. So that would be really helpful to have more detections in globular clusters. That's for sure.
Okay, thank you. Any more questions? On Zoom or here? I might have one, if I may. So I find it really hard to believe with so many RR Lyrae stars that none of them were found in a binary system, which would be perfect for you to measure the mass, right? Is it some kind of an observational bias, you think, or these periods are too short, or what's going on here?
So there are candidates.
Okay.
And Gergely works on them. So there are candidates that are far based on this light time travel effect. So the frequencies shift due to the movement, but they are not in a eclipsing system, so they are useless for the mass.
Well, so how about non-eclipsing systems if you have them face on, but then, for example, Gaia astrometry can give you if you have binaries with our Lyrae star, and then there is astrometry from Gaia, do you think that would help?
If the astronometry would be good enough, like majority of the stars are from bulge. So.
Well, our Lyrae are not only in the bulge, right?
Yeah, so yes, that would be helpful. Yeah, but it's not that they don't exist in eclipsing, in binary systems, but and also those systems have long periods and they are very far away. the components are very far away, so there is a bias towards that.
That's right. But, there also are Lyrae outside of the bulge, right? And some of them will be, for example, published by Gaia and other surveys, and they don't have such a superb cadence. You need superb cadence. So are there plans to do, because they're always there, right? You can conduct very high detailed photometric observations, right? Are you planning to do so? Or?
So there are people working on that from astrometry. So I'm waiting for the results from the DR3.
Cool.
So they want to combine astrometry to find the binary systems and with our layers.
Okay, good. Any other questions, comments?
I might have one.
Right.
So thank you for this very nice talk. And I have a question about the last slide. So I don't know if I didn't catch that, but why do you think there is this change in results regarding that model you have mentioned at the very end?
With the masses?
Yes, yes.
So that some stars have higher masses? You mean that one? Or...
Yeah, I guess so. I mean, there's like a little.
Oh, yeah, that one. Okay.
Yes, yes, exactly that.
Yeah, so there are everywhere different assumptions, obviously. So, so we have some different models for the evolutionary tracks. So we have evolutionary models that have some assumptions during the evolutionary track, and we have envelope models that completely disregard the interior of the star. So there are, so there are different assumptions behind, and the third method here that matches the physical parameters. This is based on completely different modeling of shapes of the light curves. So there are completely different assumptions there. So basically, we should work that it matches, but I don't know where is the discrepancy, but it will be very interesting to find out.
Okay, thank you so much.
Okay, thank you very much. I don't see any more questions and comments, so let's thank our speaker again. Thank you very much.